few tries to get the live streaming going right. Thank you if you waited around for that. So in the previous episode, we unwrapped the electric eel instrument for the first time after it had been in storage and tried to get going again. And quickly found out that the circuit board had, see right there, someone had written, probably me, burnt out on there. So that chip had been burnt out, and in the next episode after that, I did some surgery on that dip chip that you see right there. I replaced it right where it is. And now, what we're going to do is we're going to see if we can actually run the CPU board. So this is the electric Eel CPU board, based on the Atmega 32. Now you'll recall maybe that I said that when this board here was broken, it was driving all of the input voltage from the generator through to the CPU. And I felt pretty sure that that had burned out the CPU. But I just wanted to take a look. So the first thing we're going to do is we're going to hook up a serial port to the synthesizer board by itself, just to see if that works at all. And if that works, then we'll connect the regulator up and see if they work together. Alright, so first, I'm using one of these. You don't need this part here. This is from a consulting job I did for Mr. Dan Goldwater a long time ago. Shout out to Dan. Anyway, this is your common FTDI serial port that's got 6 terminals here. And this is a 3-volt one. And it plugs right into the electric eel here. Notice how the electric eel has, just make that in focus. Yes, that's nice. A black line right here on the circuit board. So that's telling you that's where the negative terminal is. And coincidentally, on this connector, you can see the black wire, black is often ground, has a red stripe on it to indicate that it's pin 1, and that's usually ground 2. So now this thing is plugged in to my computer serial port. So over on my computer screen, I'm starting GTK term, just because that's what I use on Linux. There are a bunch of other term programs. I like this one because it's graphical. So the first thing is, I'm going to adjust the camera so you can see the screen there. There we go. So the first thing I'm going to do with this board is simply flip this switch here, because these... Oh boy, hope that didn't make you dizzy. Knock the phone right off the stand there. Okay. So anyway, this serial cable has a 3-volt source right inside it. I think it's actually this red pin here. So that's 3 volts. So the way this board is designed, you can connect one of these serial ports to it, and then you flip this switch. Aha! And see how the light came on, and in the background, we got ourselves the electric eel debug prompt. So what is that? That's where, that's a key thing for restoring these things, and also when you're designing them, so you can see, you can interact with the device over the serial port. So I can't remember any of the commands. It's been too long. The only one I found is D, or was it A? Yeah, and A is showing us all the values on the analog to digital converters on there. So let's just make this window a little bigger. Can't see it very well there, but what I'm going to do is just put my fingers on all the pins. So on the circuit board, normally you need a somewhat high impedance, somewhat low impedance drive on these. But for our purposes, we could just use the hand and see if we get any sort of value on there. And so yeah, you can see up here we're hitting values in the 600s. And then I'm going to take my finger off, and we see that the ADC values go way down to 0. So we're having some effect on this board. That's pretty good news. Okay, that's the first part of this. What are we going to do next? Let's go back. And what does this tell us? this tells us that the board is actually halfway working. I was pretty certain, remember, that I'd blown out this chip with a bad voltage regulator, but apparently we haven't. So now let's do something. Let's take it to the next level. First, I'm going to turn off this switch. So now this guy's not going to power up unless he gets voltages on his input terminals there. So what voltage is on those terminals? Well, here's a hint. Black is almost always ground or negative or zero. Red is almost always non-zero or power even, like +5, +3. In this case, this board is designed so that one of these is the voltage in to drive the CPU, the regulated 3.3 volts, and one of them is the output to go out to the synthesizer board. And they're labeled on here. A little hard to see maybe with the tube in place. But looking at the side, I could see that that one has that's the power in. Can we focus that close? Almost. Anyway, this side is the power in. So let's switch our attention over to this regulator. This board also has its pin out explained on it. So you can see right here, this first pin is V in. This is ground, ground, and this is the regulated voltage out. So basically it's large DC voltage in, ground, ground, CPU voltage out. Okay, so again, you see that that's ground, the red is a voltage, and the red is a voltage. So our job is to connect the 3.3 volt output from the regulator to the synthesizer. Okay, remember this is the power in here. So this board has a modification on it. This is hard to believe, but when I first designed these boards, I was actually using a 7805 regulator. Like I mentioned in one of the previous videos, that's not an efficient regulator at all. That's why we had to switch to this switcher. But we can tell from the footprint what the pinout was, right? With the those regulators, the LM7805 pins 1, 2, and 3 are voltage in, ground, and voltage out. So this used to run at 5 volts. It didn't even run at 3 volts like we're going to run it today. So all these things are just because this is the very first generation of these things. And as I was designing it, I kept realizing new improvements to make here or there. And I knew I had to limit my improvements. Let's see. So I'm using that green as ground. And then we found that the yellow was there. That's the 3.3 volt output. Okay, so those are firmly in place. This blue one we can use later. That's to actually measure the incoming voltage so that we can give some expression to this instrument so that the CPU can see when the player is playing very fast and very hard. Because that'll create a large amount of voltage at the input of the generator. And then even though the generator sends over a regulated 3 that it can run, it also tells the CPU, through this voltage divider, what the incoming voltage is. So we'll get to that. It sounds great. It's amazing. It was a very late innovation, obviously. But it was a mod that was made to many of these instruments to make them more expressive. But we're going to leave it off for now because we don't even know if this regulator... I don't know if anyone remembers, but first of all, we're seeing a voltage of 3.1. And second of all, it started around 3.17 and slowly wound up. You can go back and watch that video if you want to see the spookiness of that voltage regulator. So given especially that spookiness, we're going to play it safe here. And I'm going to use my, my power supply here. And I'm going to give it a nice, predictable 5 volt a 5 volt voltage source, right? So we're regulating from 5 down to a nominal 3.3, although in experience we've seen 3.7. Let's just see what happens. So first, turn that off. All right, so if this works, I would expect that when I turn this power on, it's going to put a 3.3 voltage there, and that's going to power up this CPU. And then we may even see something over on the serial terminal. Now, we know that if we just flip this on right now, we see stuff from the serial terminal and the light goes on. because that's the mode where it's getting the voltage from there, from the FTDI serial cable. But if we turn that off, now we just have gobbledygook on the screen. So it kind of reacts if you press a key. That's just electrical artifacts. But when we turn on this bench supply, it should be regulated to 3.3 and turn on the CPU. And then, let's see what we can see. Ready? 3, 2, 1. Okay, so I'm not seeing anything on the serial port, which probably means that we didn't get... it could mean the chip is flaky. Could mean a lot of things. But let's just check our wiring here. Oops. So turn it off for a sec in case something bad happens. So this yellow, that's supposed to be coming from here. And this green, that's supposed to be connected to there. Alright. And then let's check the input as well. That's supposed to be a ground there. Yep. And that's the voltage in. Alright, so let's fire it up again. Okay. Nothing out there. Oops. In serial port land. So what I'm going to do is I'm going to get my voltage my voltage meter. And let's look around on the board and see where the voltage is. Okay, so there's the trustworthy digital multimeter. Can you see that? So I think the first thing I want to do is just look at the output of the regulator by itself. Just see, are we still getting those 3.7 volts that we thought we were? So fire that up. Okay, so that looks good. We are seeing 3.7 volts there. All right. So that's good. But we're not even getting this bulb to light up. You know, like when we have that there. I wonder why that could be. So we know that the chip seems to run when it gets an input voltage. Oh, you know what it is? Actually, I don't think that... Right. Because we've taken this, this 7805 regulator out, I think we're actually using the other pin, pin 3, to power it. Okay, yeah, so that means we don't want this yellow one here at all. Okay, that's actually the V in that gets measured. And this is the one that goes to the supply. Alright, so let's turn that off. Plug it in. Plug the CPU in to the proper place. Alright, now turn it on again. Ah, there we go. Beautiful. So we see the light is on. The debug prompt is on. You can run that A command. And we're running completely off of the benchtop power supply. So if I hit stop, start it, comes right back up. So that's pretty exciting. We can still do the A. So that tells us our second piece of good news. That tells us that the circuit board for the power supply is working good enough and the CPU is working good enough now. One thing I'd like to know is the chip actually putting out a signal that would trigger an amplifier? In other words, are we seeing some kind of square wave or something like that? So what I want to do is take a look on this board. If this was this is the power in signal. This one here is actually the audio out. So we could see if this chip is generating any synthesizer sound. Maybe hook it up to an amplifier. Let's hook it up to a scope first. Okay. So I just happen to have this little scope here. And I hooked it up before I did this because I'm not sure that's very exciting watching people just hook up scopes. I don't know. You tell me. In this case, I'm gonna, oops, over on this side. So that's the audio out. That's the ground. All right, and look at that. Already I am seeing some kind of a signal there. Tell you what, let's turn out the lights just so you can see it really well. Yeah, okay, that didn't work the way I thought it would. So we've definitely got some kind of square wave looking signal in there. I think those are actually PWM spikes too, because the synthesizer algorithm relies heavily on a combination of PWM and varying input voltage to make it sound. Gee, this is fun too. We can also see the current we're using, 42 microamps at 5 volts. So on the supply side, that's a total of, what, 210 milliwatts? Okay, that's not too much, not too little. You know, we'd always like to use fewer milliwatts. How much louder could we make the speaker, and how much longer could the CPU run? But for now, let's skip the design stuff. Let's see if we can hear this sound. So the way I hooked this up, I connected the scope and the dev board up to a 1/4-inch jack header, and then that is going into my guitar amp. So let's find that. Okay, is it this cable? Turn that up. Yep. Okay, so now, alright, this could be very loud, I don't know. So we're going to plug that in. Oh yeah, so we're already hearing some sound. Okay. So we're able to, hang on. So normally in operation, the synthesizer chip on this port here reads the knobs. Actually, we can disconnect the console for now. We know it's working well enough. There we go. So normally in operation, it reads this one to get the keyboard signal and this one to get the knob signal. Or is it vice versa? Yeah, so take a look on the oscilloscope over there. You can see how the signal's changing. Because when I put my fingers on these, it thinks that it's someone playing with the knobs on the instrument. So that should translate into a pretty crazy sound. Well, it's... Anyway, so that's a good result too. That means that this board here is intact enough in this CPU that we could hook up a keyboard and we could hook up a knobs and then we can hook up an amplifier and whoo, maybe we'll actually have an entire instrument. So I guess that's what's going to happen in the next episode. The other thing we have to do is hook up the generator on the input here because, I mean, let's face it, anyone could just run with a power supply going on all day. So let me just, I'll tell you what, let's just try this. If you've watched this video this far, I think you deserve a treat. So I'm going to go get a generator. Okay, so this is a 2-part generator from another instrument. You've got this slider with the stepper motor on the back, right? It's being back driven. And that's connecting to this gigantic piece of generator electronics. And then, which pins are the output here? So that's also written on the back of this module. You can see right here on the left. That's the power out. There's the audio in, incidentally. But let's concern ourselves with this power out. I didn't check to see if this thing works, so I don't know. But let's just try it. So I'm disconnecting the benchtop power supply here. Inserting the generator, the input. Now if this works, a couple things will happen. We'll see the light up on the synthesizer, and we should see some output on the console as well. The scope will light up too. Let's see, I can't even see everything, but there we go. Alright, let's give it a whirl. Ah, yeah, that's a great sign right there. You see that? Blue light is staying on as long as the CPU can. Now let's look over at the serial debug port. Whoop. It's a little hard to see. Oh, that's right, we disconnected it before. Alright, let's just assume that's going to work. Because also, we look over at... Look at that, we see the waveforms coming out of that thing. So we could even hook up the amplifier just as a test. Okay. Alright, so right now the CPU is off because the capacitors are all drained. But what's going to happen is I'm going to hit the generator and... Whoa! That's incredibly loud. Alright, sorry neighbors. I'm just going to make one more sound for silence. With this connected. Oh boy. Alright. So thanks for joining in. That was really fun. You know, we at least have the generator, and I don't want to test the amplifier right now because I'm not really set up for it. This is just a little tiny part of the bench. But let's save that for next time. And I have to find the keyboard. You know, I didn't have the keyboard at all for this thing. I've been looking through my stuff, a lot of old boxes. I don't know where it went. I don't know if it's in another instrument. I kind of doubt it. It's just in some stuff somewhere. I've also been pondering whether or not I should make a new one for this instrument. So anyway, once again, if you like this kind of stuff, definitely like and subscribe. Get in on all the action. Get some influence on the design. Learn how it's designed. Learn how to restore these things. And get some insight on the next generation of generator instruments. Yes, it's true, there are plans for a second generation of these things. So in a way, restoring these is kind of a warm-up. We'll get into that later. Have a good night, everybody. Thank you. Bye.